There's no one really better qualified to start us off on this weekend than Warren Brown, who is Professor of Psychology at the Graduate School of Psychology at Fuller Theological Seminary, where he's director of the Lee Travis Institute. He's also a member of the UCLA Brain Research Institute, and he's actively involved with experimental neuropsychological research related to the functions of the corpus callosum of the brain and its relationship to higher cognitive processes in humans. He's particularly interested in how all this feeds into Christian belief, and he's written various books on this and edited books on this, and in particular the one with the title I've got tonight, Did My Neurons Make Me Do It? That is on the bookstall. And I think without further ado, I'll let Warren speak to that title. Thank you.
Thank you very much. I appreciate Rodney and Dennis inviting me to do this again. It's a particular honor to be invited back. I didn't mess up too bad the first time. This may not be as exciting as the Roddick Murray tennis match that some of us just watched, and I know it's after dinner and some of you are tired from travel, but we'll try to make it move along. If I'm not talking loud enough, or if I'm talking too fast or something, raise your hand. A lot of what I'm going to say is on the slides, so that you'll have two chances to know what it is that I'm talking about, both what appears in the text and slides and what I'm saying. So that will allow you hopefully to follow better. Let me start with a familiar verse from the Psalms. The verse is, "When I consider your heavens, the work of your fingers, the moon and the stars which you have set in place, what are mere mortals that you are mindful of them, human beings that you care for them." And that's a nice verse with respect to cosmology, but for the purposes of neuroscience, one might say something like this, sort of the modern question of human neuroscience. When we consider the brain and the rapidly growing knowledge in neuroscience, what is it, if anything, about human nature that has theological significance, that is important to us in our understanding of the relationship of religion to human life and human existence? So that's just kind of my introduction to the topic we'll be considering throughout the conference. My role in neuroscience, Rodney gave you a little bit of this. I'm a research neuropsychologist. I'm not a theologian or a philosopher, even though I'm from Fuller Seminary. And I study the cognitive and psychosocial consequences of agenesis of the corpus callosum. I'll show you what that means in a minute, just for your curiosity. And I'm a professor at Fuller Seminary in the Graduate School of Psychology. And the fact that I'm doing this kind of neuropsych work at a seminary puts me in an interesting position in the world. I think I'm the only neuroscientist in the world that has a faculty position in a theological faculty. We have a graduate school of psychology, so we're educating clinical psychologists. I teach the neuropsychology or neuroscience part of that curriculum. That's how I end up at Fuller. But it does put me right in the middle of these conversations about the relationship between neuroscience and both philosophy and theology, which has allowed me to do some work that I'll talk about today. So what is that I study, just so that you know? I study agenesis of the corpus callosum. A normal corpus callosum, normal is in quotes because this is my corpus callosum, is right there. It's that white structure that looks like the head of a hammer, and it's 200 million neurons that interconnect the right and left cerebral hemisphere. We study people in the world who are normally functioning, have a normal IQ, but have agenesis or absence of the corpus callosum. So if you see right there, there's no corpus callosum. 200 million neurons are congenitally absent, and we look at the consequences of this for psychological, cognitive, and social functioning in these individuals. Quite interesting work. It's not particularly relevant to what I'm doing, talking about today, but it is what I spend my time doing. So some of the issues that we want to talk about in human neuroscience and religion, at least the two I'm going to talk about, is the nature of free will, and that we'll talk about tonight, and then tomorrow I'll talk about the nature of human morality. And so those are the two topics that we'll try to work with within the context of neuroscience. The work I'm going to talk about today came out of a book that Nancy Murphy and I wrote called Did My Neurons Make Me Do It? This was the subtitle is Philosophical and Neurobiological Perspectives on Moral Responsibility and Free Will. And the neuropsychological or neuroscience aspects I'm going to take up today, I will leave the philosophy to Nancy Murphy. So I'll try not necessarily to make philosophical arguments. We may go there, but it's not my intention today. So the outline of what I want to talk about today, I'm going to first talk about some of my assumptions and hypotheses about human beings as well as free will. I'm going to talk about action loops and nested hierarchies as one way to think about how you might have something like emergent agency and free will. I'm going to talk about frontal lobes and prospective action, prospective control of action. So if you're going to be a real agent in the world, you have to have prospective aspects of your behavior where you're looking ahead. I'm going to talk about complex dynamical systems and emergence. And then I'm not really going to talk about, other than just to mention the role of language in this, you really can't talk about higher human agency and moral responsibility without talking about language. So we'll talk about a little bit, much to say, but not much time to say it. And then just some conclusion remarks. So first, assumptions and hypotheses. My basic assumption is that the human mind or soul is embodied, is a property of our body. Dualist argument. So this is a non-Cartesian point of view, that we are embodied persons, but we are also embedded within social context. So what that means is we have the person, and the fact that we are physical beings means that we have capacities of persons that are dependent on or emerge from our physical nature. So you have emergent or embodied properties that go down to the level of biochemistry, and then there are neurons and cells that organize out of that, and then body and brain systems, and then neuropsychological capacities, and all that comes together to subserve an embodied person. But we are not only embodied, we are embedded. That is, we are embedded in immediate social context, the people we were around at the time, our social histories, and our cultural embeddedness. So we are affected then both bottom up by, and we are a agent in affecting things in social context, but also affected by our bodily systems. You call that bottom up, but we also have top-down properties. There are top-down properties from our embeddedness in our social culture. There's also what we'll talk about as top-down properties or top-down influences from us as whole persons to the way that comes out in terms of our neuropsychological capacities, brain systems, and so forth. So another assumption is that I alluded to before is a assumption of embodiedness, and the term that Nancy and I use is non-reductive physicalism. By that we mean, by physicalism we mean it is not necessary to postulate a second ontological entity, the soul or mind, to accommodate for human capacities and distinctiveness. Soul and mind are physiologically embodied. They're part of us as physical persons. Non-reductive means that human behavior cannot be exhaustively explained by analysis at lower levels. Higher level causal properties emerge, top-down causation exists, thinking is efficacious. Now, as a terminology, we consider this philosophically explicit, but I consider sort of a minimalist statement. That is, it's an explicit statement of the fact that we are physical and the fact that we have properties that are non-reductive. Other people use terms like emergent monism. Monism being we are one thing physical, but we have emergent properties that are non-reductive. Only problem with that is it's not philosophically explicit, because you could be a monist and be an idealist, not a physicalist. So, and then there are emergent dualists and so forth. This is does not exclude any of those possibilities. It merely gives a minimalist statement of what we consider to be a philosophical position. The problem with physicalism as a position on human nature is the problem of determinism, or determinism and reductionism. And this is the way my colleague Nancy Murphy expresses the problem of determinism. If mental events are intrinsically related to neural events, how can it not be the case that the contents of mental events are ultimately governed by the laws of neurobiology? That's our primary problem today. If neurobiological determinism is true, then it would appear that there is no freedom of the will, that moral responsibility is in jeopardy, and that our talk about the role of reasons in any intellectual discipline is misguided. If everything is determined at the law of physics, even our reasons for believing they are determined at the law of physics are misguided, because that mental state is itself determined. Here's the way Douglas Hofstadter, in his book called The Strange Loop, makes the same point a little more literally. Is what goes on inside our heads just a deterministic physical process? If so, are we all, no matter how idiosyncratic and sparkly, nothing but slaves to rigid laws governing the invisible particles out of which our brains are built? Could creativity ever emerge from a set of rigid rules governing minuscule objects? Can mind emerge from a physical system? So some of our questions are, if we are physically embodied beings, is it inconsistent or incoherent to say that we consciously and willfully cause our own behavior? In what ways are biological systems self-causing agents? How does a complex biological organism become a morally responsible human being? Won't answer all of those questions fully, but I will give some resources that I think move us in the direction that we need to go. The critical answer in a nutshell, but in a sort of gloss, in the sense that I'm not yet, I'll try to make this term more specific as we go along, but the idea of emergence, which my definition is, it denotes the fact that causal entities, that complex entities can have causal properties that do not exist within and cannot be reduced to the properties of the element that make up the complex entity. So a complex entity, as a complex system, can have causal properties that you cannot reduce to the elements within that complex system. So here's some of the resources. Let me first talk about action loops and nested hierarchies as a way to understand the mind in relationship to the brain. The models of mind that come out of much of philosophy of mind are sort of linear models which talk a lot about brain states and mental states and how they are related to each other, so that the problem is set up this way. You have brain states leading to the next brain state, leading to the next brain state. There are tied to those brain state mental states, which we experience. And so, but the question is, do the mental states themselves do any real work, or are they redundant? Is there, in fact, some way in which a mental state affects the next mental state, or a mental state affects the brain state? This is the way Jaegwon Kim philosophers set up the problem and obviously came out to the conclusion either you have to get rid of mental states or you have to be a dualist because it's overdetermined, it's a redundant system. You already have the chain of cause that you need. Mental states have no causal property. The problem with this for me is that it's linear. And I don't think our systems work in this kind of linear way, state to state to state. As if, for example, you could stop the system and say, okay, what is the next state going to be? In fact, I get a better idea from Donald Mackay. I spent a year with Donald Mackay, who was at Keele University for a while. I was with him when he was doing his Gifford lectures, and this is out of a book called Behind the Eye that is the summary of his Gifford lectures. And he talks about systems as loops or action loops, and this is a diagram he created of what he calls the minimal functional architecture of an agent. And so what you have here is you have the field in which we are operating. This is the environment. And we have effector systems, things that do things to our environment. But those feed back to our receptor systems to monitor the effect of what we do, and that is compared to is fed to a comparator that compares what actually happened to the goals of that action, I sub g. And depending on that result, we have some change in the organizing system, which changes what we do in our effector system, which affects the environment, which feeds back. And this is a constantly operating loop. There's no linear system here. It's a constantly active feedback system. An example of this on the most basic level is a thermostatic system where you have a heater that heats the room. You have a receptor, a thermometer that senses what the heat is. You have a comparator that it compares to a goal state, so you set the thermostat at some temperature. The thermostat, depending on whether it's above or below this level, turns the switch on the heater on or off. That's your organizing system. Your effector system is the heater, and so forth. So you have a thermostatic system, and Mackay would argue that that is a rudimentary, smallest example of a system which is an agent. It does something in the world, and it does something in the world because of the way it's organized, not because of the specific parts themselves. It maintains a temperature in the room because of the way the system is organized or connected, not something that can be reduced to specific parts of the system. Well, that's fairly minimalist, but this is not unbiological. So, for example, there is the monosynaptic reflex arc in the spinal motor system, which operates very much like this. So here's our spinal cord, and here is the alpha motor neuron that causes a muscle to contract. Now, if the problem is to keep the arm, let's say the forearm, in a fixed position despite changing weight, when weight is put on there, it puts a stress on the muscle, particularly on the intrafusal muscles, which sense the fact that there is stretch occurred. It affects this little muscle spindle sensory system that sends an afferent fiber back and has a monosynaptic input to the alpha motor neuron, facilitating it and causing the muscle to contract a little bit more in order to accommodate for the weight that has been put on the arm. And so what you have here is not a static system, but a dynamic system, which in fact there is constantly going feedback loop between the muscle and the neural control in the spinal cord. Now you remember we had I sub g on the goal state hanging out in space on the last one, and you have also in the system a thing called a gamma motor neuron. And the gamma motor neuron feeds in and sets the goal state by causing the intrafusal muscle fibers to contract or relax. So you have a way for a goal state to be set. Once the goal state is set, the thing operates in its own feedback loop. Mackay, in his way of looking this, talked about what does it take to set the goal system. To set the goal, you need a supervisory system. You need some kind of system that feeds in to create the goal state. And then he thought about what is a supervisory system. Well, a supervisory system is really a meta-comparator and a meta-organizer. So we have our original loop here with the comparator and organizer, but that is controlled by an outer loop that is the meta-comparator and meta-organizer as a way to set the goal state. And Mackay argues that you can think about this in as many different levels as you want. So you can have meta-meta organizers and meta-meta comparators and meta-meta-meta organizers and meta-meta-meta comparators and so forth. And lest you think this is not the way that the nervous system operates. This is a version of this that Malcolm Jeeves and I created. This is from a book we just published called Neuroscience, Psychology, and Religion, but we just sort of redrew Mackay's diagram. So you have action in the world here, you have sensory feedback, comparison with goals, motor adjustments, action in the world, so forth. And this is an action loop, which we call the action feedback evaluation action loop. That's also terminology used originally by Nancy Murphy and I and did by Neurons. So things are going in these loops, and they're constantly active loops that are modified by changes in goals. And these loops we've been talking about on the spinal cord are actually set within higher level of control that works up, not only that works up the spinal cord, but then once you get past the spinal cord, then you have systems in the brainstem that modify things going on in the spinal cord, which are involved in monitoring this action loop. And then things going on in the midbrain that are modulating and modifying things in the nuclei in the brainstem that control the action in the spinal cord. Things in the thalamus that should probably also include the basal ganglia as sort of diencephalic nuclei that interact with the brainstem and midbrain, and interact with the brainstem and interact with the spinal cord, so forth. So you have a nested hierarchy of control loops. At each level of the control loop, you have a higher level of goal being monitored and set for the system. Each level higher has a control that has a higher, more complex level of control. Lest you think this is entirely fictitious, here's our monosynaptic reflex arc in the neuromuscular system. We talked about the importance of the gamma motor neuron setting the goal state for this system. Well, the gamma motor neurons are known to be controlled from above at the level of the brainstem by the vestibular nuclei, by the neocerebellum, and by the cortex, and probably also by areas in the basal ganglia that are facilitatory to the gamma motor neuron, and areas that are inhibitory. So you have a hierarchy of inhibitory and facilitatory influences coming down the gamma motor neuron. Gamma motor neuron sets your desired muscle contraction against whatever the load is at the time. So the point here is that you have a low-level system being modified not only by a number of kinds of influences of this kind in the spinal cord itself, but in the area of the brainstem and midbrain and so forth. Now back to this diagram. Whoops. We have these levels of systems, and up here at the top we have the cerebral cortex. And if you think about the way the cerebral cortex operates, it does the same sort of a thing. That is, we have the external world and the brain stem and the lower brain structures that modify it. But when you get to that cortex, the highest level on this slide, you in fact have the same kind of thing where you have primary sensory and motor cortex forming one level of control, association sensory and motor cortex, adding more sophisticated levels of goal setting, and polymodal cortex and the prefrontal cortex, even more sophisticated or more complex levels of goal setting. So, so the hierarchy levels, I wanted to give you an experiment now at the level of the cerebral cortex, which gives us somewhat the same kind of a message. And this is a work that published in Science several years ago. And they had three kinds of experiments they did. One experiment they called sensory control. And in this experiment, people were in the imager having a brain scan with functional magnetic resonance imaging, fMRI. And the simple task was, whenever a red light occurs, you hit one button, response 1. Whenever the green light occurs, you hit response 2. So you have 2 buttons and 2 lines, and they're consistently mapped, so you have sensory control. The color of the light tells you what to do. The next level was what they called contextual control. So now the context is represented by the black box. So if it's in a black box, then a red light leads to response 1 and a green light to response 2. But if the context is a yellow box, or orange box, then a red light leads to response 2 and a green light leads to response 1. So what you do with the red and green light has to do with what is the context in which the red and green light, in fact, are occurring. And then, in fact, it gets worse than that. It calls what it calls episodic control. So in block A, so one block of trials, you have what we were just talking about, a black context, red light leads to response 1, green light leads to response 2, and then if it's a yellow or orange box, you have the opposite. But then you have a next block of trials in which the contextual relationships are reversed. So this is episodic in the sense of this series of trials, this episode, you have one left set of relationships, and this series of trials, you have another set of relationships. And then they looked at the implications of this for the way the brain is processing information. So the outcome of this was that stimulus control activated the premotor cortex, and as you went from stimulus control to contextual control, you now have the caudal dorsolateral prefrontal cortex, an area just in front of the premotor cortex, begin to be activated as well as the premotor cortex. And then as you went to episodic control, now the rostral part of the dorsolateral prefrontal cortex became activated. So in each of these levels of complexity of activation, or complexity of decision making, the more frontal parts of the cerebral cortex had to be involved. And if you look at the relationships, that this is fMRI coherence measures, you look at what areas seem to be interacting with what other areas. The primary interactive system is at the level of the premotor cortex for stimulus control. When contextual control gets involved, now you have both the premotor cortex and the caudal part of the dorsolateral prefrontal cortex involved. And when you have episodic control, you have the rostral, caudal, and the premotor cortex all involved. Now these are not fMRI images. If you know fMRI, in order not to violate the copyright issues, I redrew them on my own map. So fMRI doesn't exactly look like that, but that's pictures of representation. So the schema that they drew from this is that if time is going along this way and stimulus control is all that's worried about, you just need to have the control of the premotor cortex. And so you have this simple loop between the stimulus, the activity in the premotor cortex, and the response. But if context also needs to be involved, then the caudal lateral prefrontal cortex needs to modify or modulate things going on in the premotor cortex in order to take into account the context. And if in fact episodes are also important, that which block of trials this is, then the rostral areas of the lateral prefrontal cortex are necessary to modify the caudal areas of the lateral prefrontal cortex, which modify the premotor cortex, which allows you to make the correct decision given all the contingencies that are involved. So the point is we have nested hierarchy of control that as the hierarchy goes more forward in the frontal cortex, it takes into account more information about the trials and things that are temporally distributed more. So the episodic control has to do with information you got at the beginning of this set of or block of trials versus information you got on the next block of trials and so forth. So it operates over a longer period of time. So my summary of this part about the idea of nested hierarchies rather than linear understanding is that the brain is organized in a cascade of control or feedback loops, that each higher level embodies more complex criteria and goals, that lower level systems are modulated by higher level systems in a kind of one form of top-down, physically top-down, but also in complexity top-down, and that the highest levels of cortical control involve long-term episodic and semantic information. So if you look at least that last experiment, an episodic control is an issue that is episodic temporally and semantic in terms of the kind of information that has to be held in mind in order to make decisions at various points in time. So that's the first resource that begins to open up neurobiology from a determinist and reductionist paradigm to something that looks more like agents and willful agents. The second is to look at the frontal lobes. We've already begun to talk about the frontal lobes, but look at them more generally in terms of what kind of things they do. The frontal lobes are a good place to look for things that are uniquely or distinctively human, in that the frontal lobes are noticeably larger in phylogenetic comparisons. So a squirrel monkey has a very small, as does a cat, small prefrontal cortex. Rhesus monkey larger, dogs a little bit smaller than a rhesus monkey, a chimpanzee a fairly large prefrontal cortex, and human beings the largest prefrontal cortex. And that's true both absolutely and relatively. In fact, it's more true relatively in the sense the relative size of our prefrontal cortex compared to the rest of our cortex is distinctively not on the same scale as that of the chimpanzee or monkey. Joaquin Fuster at UCLA, one of my colleagues at the Brain Research Institute when I was there, was studying the prefrontal cortex, wrote a book on it. He thinks that the basic properties of the prefrontal cortex are the following. First of all, temporal integration of behavior, the ability to integrate behavior over longer periods of time. You've got to be able to extend behavior and behavioral control over longer periods of time to be a meaningful agent. The idea of working memory, that is to bring back into remembrance information from the past that is relative to the current situation. Third is attention, the ability to control what one attends to in any particular situation, so you focus on that and not on something else, depending on strategic goals. Preparatory set, to be ready given the current information or the current context to act in some way that is relative to the information present at the moment. So it's a prospective part. And the last is inhibitory control, the ability not to do things that might appear possible. Or so, example, in the episodic control thing, I know you've got the tendency to press the wrong response button given that light in the context, and you've got to inhibit the tendency to do that in order to take account of what the current context and current episodic situation is in order to make the right response. So generally then, to summarize that, the prefrontal cortex allows adaptability over time, incorporating both a retrospective, that is memory, and a prospective, preparedness for action and anticipation of outcomes, aspect into the control of behavior. So the prefrontal cortex allows us both retrospective to bring back from working memory, back from memory into working memory, things that are retrospective with respect to the current situation, and prospective things, and that is the ability to prepare for a series of actions that will extend through the future. Just an example, we'll talk more about Phineas Gage next tomorrow. Phineas Gage is the most important case in neurology of the prefrontal cortex. Phineas Gage was working on the railroad in the 1880s and tamping an explosive charge, and with a big, thick, long metal rod, the charge went off and blew the rod right up through his eye socket out the top of his head, and basically destroyed the frontal lobes and the medial frontal cortex in that area. So I just kind of drawing arrows in approximately where that went. The interesting thing about Gage is after the accident, he became unreliable and capricious. You could never tell what he was going to do. In fact, there was a disconnect between what he said was the right thing to do and what he would actually do. He became socially inappropriate, so you never could tell socially whether he was going to do something inappropriate or something appropriate. And he became amoral, not necessarily immoral, but there was just no moral anchor to the behavior of Phineas Gage after this accident. Prior to this was not the case. So you can go to the clinical literature and find some important things about human agency that get disrupted when the prefrontal cortex is not operating correctly. I want to give you another example of an experiment, and this is an experiment from Hare, Camera, and Rangel. They are Colin Camera and Rondell are people at Caltech that I interact with some, and Fuller is actually just a mile or two from Caltech, and so we do some work together. And this is an experiment on dieters. So they had 36 individuals who were dieters as participants in this experiment, and each of them rated 50 food items for taste and for health, whether this is a good thing to eat on a diet or not, and also is this something I really like or not. And then each was given a series of preference choices with respect to a neutral item. So there's a neutral food item and one of these other items, and you have to choose whether or not you'd eat the neutral item or this other item. And this had real consequences because some percent of what their choices they were going to actually eat later. So this wasn't theoretical, this was actual choices. And the participants were divided into a self-control group, that is, people who rejected tasty but unhealthy foods when given the choice, and non-self-controllers who predominantly choose based on their taste preference. So you had healthiness preferences and taste preferences. People who aren't very good at dieting just always chose based on taste, and those who are better at dieting, self-control people, use both health and taste. And then they did this in a scanner. And so what they found was a number of things. First of all, the ventromedial prefrontal cortex, the area where the damage to Phineas Gage occurred, the activity in that area was correlated with goal value or preference. Whatever your preference was, the more you preferred the item, the higher the activity in the ventromedial prefrontal cortex. Activity in the ventromedial prefrontal cortex reflected health ratings only in the self-controllers. So the people who were not able to control their diets, their ventromedial prefrontal cortex only reflected their taste preference. People who were controllers on their diet, the activity there reflected both health and taste. Now, just as an aside, our understanding of health is something we learn through basically verbal communications with other people who tell us what we need to do, what's better to eat, what's not to eat, so forth. So it's something that starts out socially as a interaction with other people, primarily linguistically, on the basis of which eventually, if we're able to take it into account, our ventromedial prefrontal cortex will reflect that preference based on that. Also interesting was that the dorsolateral prefrontal cortex was more active during successful versus failed self-control. So if you are successful at controlling your choices, your dorsolateral prefrontal cortex on that trial was more active than on trials in which you were not successful. You chose an unhealthy item just because it tasted good. And of course, the people that were not good controllers had less dorsolateral prefrontal cortex activity because they were making all their own choices. And then the other thing was that you could demonstrate functional connectivity between the ventral medial prefrontal, between the dorsolateral prefrontal cortex and the ventral medial. It wasn't direct, it was via another nucleus, but it was clear that these areas in the dorsolateral were affecting the ventral medial in this situation. So again, you have a set of criteria in the ventral medial cortex that have to do with taste, or maybe taste and health. And then you have the dorsolateral parts of the prefrontal cortex having an influence on those with respect to changing the value activity in this area that would then reflect your choices. Again, Phineas Gage had this area damaged, and so his choices didn't reflect much of anything. They were just capricious. So, just as a way of sort of summarizing prefrontal cortex in the words of Joachim Fuster, and also as a transition, so here's the way Fuster talks about the prefrontal cortex. He says, as networks fan out and upward in association cortex, they become capable of generating novel representations that are not reducible to their inputs or to their individual neuronal components. Those representations are the product of complex, nonlinear, and near chaotic interactions between innumerable elements of high-level networks far removed from sensory receptors and motor effectors. Then top-down network building predominates. Imagination, creativity, and intuition are some of the cognitive attributes of those emergent high-level representations. Emergence is a term we talked about, so I highlighted that one, but I highlighted these because this is sort of where we want to go, complex, nonlinear, near chaotic interactions. So the next thing I want to talk about is the idea of a complex dynamical system and emergence. So we talked about hierarchies, we talked about the frontal lobes as a particularly important area in agency, and now I want to just talk about systems that are complex, whether they're brain systems or other systems. What are the nature again of these, and how might these explain some things about agency and the brain. So dynamical systems theory, I believe, can give a very good account of the emergence of causal properties within complex interactive systems. Systems that are self-modifying, nonlinear, near chaotic, so forth, based on adaptive self-organization. And I believe this comes to, at least for me, an understanding of the emergence of non-reducible agency in complex systems. So the properties necessary for the emergence of a complex dynamical system: one, you need complexity. For example, a very large number of units of neurons, elements. You need maximal interconnectivity. For example, a very large number of synapses per neuron, hundreds of millions of neurons and thousands of synapses. You need two-way interaction between elements such that you have recurrent connections and feedback loops in the connectivity within the system. And you need nonlinear interactions that amplify small perturbations and small differences in initial conditions. And synaptic systems, I think, are fairly reasonably understood in that way. So the nervous system certainly meets basic criteria for understanding it as a complex dynamical system. Just to give you an example of complexity, this is the work of Feldman and Van Essen, and this is the monkey cortex, and here's the side view of the cortex and the medial view of the cortex, and all the areas involved in vision are colored. And then this irregular shaped thing is the flattened out version of the cerebral cortex with all the colored areas that are involved in vision, or all the areas involved in vision colored. So here's V1, the primary visual cortex, here's the frontal light fields, which are generally up there, and so all these areas are flattened out. And so Feldman and Van Essen also drew the wiring diagram for this system. And this is the wiring diagram that Feldman and Van Essen thinks there is evidence for. And some things to be said about that is each one of those lines can't be one axon. It's got to be hundreds, thousands of axons, depending on which one of those lines you're talking about. The other thing to say is the complexity inside each one of those little colored boxes dwarfs by many orders of magnitude the complexity of this drawing itself. So, there's plenty of interconnectivity, there's plenty of feedback, recurrent connectivity, and plenty of complexity in the nervous system, even just taking the visual system into account. So the characteristics of a dynamical system is that they self-organize when pushed far from equilibrium. They are open systems and capable of self-organizing with respect to the environment. Elements of the system become entrained by large system patterns. So once the system begins to organize, it organizes in a way that it constrains the activity of the elements in the system, such as to create a pattern that can somehow meet the environmental perturbation. Large perturbations of the system cause reorganization, so they're adaptable systems. They can continually reorganize. Continued reorganization creates higher level of organization. So in dynamic system, when a system has to reorganize, the original organization is maintained in some sense, but it's reorganized in a way that now creates a more complex version of the in the same system that preserves many of the levels of prior organization. And then self-organization based on environmental feedback means that the system organization embodies meaning in some sense. That is, the way the system needs to organize in order to meet this environmental challenge means that something about the environment or the meaning of the environment is represented in the organization of the system. Now let me give you one example of that. I like the work of Walter Freeman on the olfactory bulb of the rabbit. And this is actually old work. Walter Freeman had 60 electrodes, a kind of matrix of electrode, over the olfactory bulb, and the event was just the rabbit smelling something, sniffing. So each time the rabbit sniffed, you get a pattern of electrical activity over the surface of the olfactory bulb. And you get areas in which there's maximal activity and areas in which there's very little activity, and you can develop an isopotential field map of the activity over the olfactory bulb. That's what you see on the right. And so basically it says that information is contained in the spatial pattern of amplitude across the cortex. So one message here is that information about smell is carried in pattern, not in specific neurons. The interesting thing to me is that we looked at this over time. So that looked at, for example, the pattern for the smell of sawdust. And this is the pattern you got, and this is a situation where the animal had some reason to note sawdust and learn to note sawdust in some learning experiment. And then after that was established, then had the animal learn the smell of banana and differentiate sawdust from banana. At that point, if you go back to sawdust, the pattern for sawdust now is different than it was originally. You now have a new organization of the system based on new experience with banana which changes the organization generally, for which now you have a different pattern of activity on the olfactory bulb for the detection of sawdust. It is experientially modified by the experience with bananas, which means the information about sawdust is not just slave neurons that have a particular relationship with an environmental smell, but a pattern of neural activity that takes into account the animal's experience with smells as well. And so these are example of self-organizing patterns in a complex system in which information is carried by the pattern, not the elements in the pattern. The change shows that bulbar activity, this is Freeman's work, is dominated more by experience than by stimuli. Otherwise, sawdust would always give rise to the same plot or the same pattern. What Freeman says about this, what is new, this was a long time ago, over 10 years ago, so not all that new now. What is new is the development of nonlinear mesoscopic brain dynamics, by which the theory of chaos can be used to understand and simulate the construction of meaningful patterns of neural activity that implement the process of observation. So you can talk about these systems now as examples of top-down causation, in which macro-level processes, as is the micro-level processes, that is the physics and chemistry of neurons, become caught up in and influenced by the larger dynamic patterns that constitute the mental or perceptual or memory event or whatever you're talking about with Walter Freeman. It was the perception of a smell. Thus, the emergent phenomena of thinking, deciding, consciousness, memory, language, representation, belief, etc. create top-down influences, that is, as larger patterns of organization, create top-down influences on the lower level physiological phenomena whose activity constitute the brain processes themselves. So you don't get past the necessity of having a physical system with lawful physical relationships at the lower level. It's just those relationships become constrained and influenced by larger patterns in which they are nested, and therefore the system operates on the basis of the patterns, the information represented by the patterns, as much as or more so than, if we're talking about higher mental activity, than the neurons themselves. The way Alicia Guerrero talks about this, Guerrero is a philosopher who wrote a book called Dynamics in Action, and takes dynamical systems theory as a basis for talking about human action. And she says the higher level of organization, whether thermodynamic and a thermodynamical system, psychological and human psychological system, or social process, possesses a qualitatively different repertoire of states and behavior than the earlier level, as well as greater degrees of freedom. So anytime the system reorganizes around new information, that reorganization creates qualitatively different repertoire of states and greater degrees of freedom for the future actions. And again, from Guerrero, how dynamical systems manifest free will, she would say that constraining variation of constituent parts by environment-related patterns paradoxically increases the possibilities for the system, that is, greater degrees of freedom. So you have constraint at the lower level allows the system as a whole to have a greater number of possibilities. Once organized, a system responds or acts from its own point of view. So in the sawdust and banana situation, the response, the relationship of the animal to the sawdust smell is really from the animal's point of view, that is dependent on its history as well as the current stimulus. A system organization embodies meaning, that the organizational patterns on the olfactory bulb, for example, is what carries the information about the meaning of the smell that was related to it. Higher and higher levels of semantic considerations can be expressed in behavior via continual reorganization, and dynamical systems manifest novelty. So if you're running these in computer simulations and you really have a dynamical system properties, there's a certain amount of novelty and unpredictability in the systems, even though they organize them to some degree predictive. So that's how Alicia Barrero talks about dynamical systems with respect to the possibility of free will in quotes, in the sense that it's not unembedded in its history, but it nevertheless has degrees of freedom that are not entirely linked to the immediate stimulus environment. So language, I told you I'm not going to talk much about language. There's much to be said, but I think it's an important part of the understanding of human beings with respect to a moral responsibility and free will. Some contributions of language to human cognition and behavior. First of all, it distances our actions from the demands of the immediate environment needs. So we can use language to represent things in the future. For example, we can use language to represent the idea of healthy or not healthy food, and that allows us to decouple our actions from immediate motivations and need, like how tasty is this thing. The ability to form a self-concept, that is to represent the self to yourself, to create a representational feedback system in which I can understand myself in relationship to myself. Expanded empathy through narrative. By the way, I think I got these from Terence Deacon. These are not my own. But the idea that we can tell a story about other people or about ourselves and understand the inner life of other people through narrative and language. And that begins to modify our behavior. A virtual common mind among groups of people. We use language to communicate with each other and modify each other's behavior in order to create some kinds of common understandings. And the possibility for ethics, that are at least one level of our ethical systems are represented in language. So my conclusions, and this goes back to the general problem of determinism with respect to humankind. I would say, and the way I would frame this, is there are three possibilities for human agency. One is humans are physical systems that are closed and near equilibrium, therefore behavior is determined by physical laws. This is determinism and reductionism. Another possibility is that humans are physical systems that are somehow open to influence from a non-material part, a mind or a soul. Therefore, humans have free will in virtue of the non-material part. This is Cartesian dualism. And then what I would say is that humans are physical systems that are open, far from equilibrium, ultra-complex, and non-linear. Within such system, properties emerge that are causally efficacious and manifest a robust and reasonable form of free will. That is the implications of non-reductive physicalism or emergent monism, or whatever term you like. So thank you. Appreciate your attention.
Thank you very much, Warren. That's got us off to a terrific start. So we've got quite a bit of time for questions. So who would like to start? Yes.
So if we can just go back to your the comparison between models, between what you call the linear model
Yes.
and
Right.
loops.
Feedback.
Yeah. They're both serial. So you can reduce the loops to the linear model simply by opening the loop, which is not how it normally works.
Yeah,
Right,
yeah.
there's
So the
lots
point
of
is it doesn't work that way, yeah.
But you've still got one event leading to another event, leading to a third event. In the case of the loop, you feed back from the event to the end to the event.
Yeah, the problem from a philosophy standpoint is to act as though behavior freezes at any point. that in fact you can sort of stop, you can act as though you could stop the system, say now you have a mental event and now you have a brain event and this is feeding forward, and which in fact there is no stop and start behavior. Behavior is always within the context of ongoing feedback, which changes the, for Nancy and I, when we started thinking through this part, decided it changes the philosophical statement, not to what precedes this, but given an ongoing system, what criteria of evaluation are being used, and how do those change? So it makes a little bit different kinds of statement. It's not that you can't open the loop in a sense. It's just that when you're thinking about how brains and nervous systems operate, they're not operating as if you can line them on one state to another, but they're constantly feedback system that what changes is criteria of evaluation. So we're not, another way to say that is we're not sitting around making decisions about our next action. What we are doing in terms of agency is deciding what are the criteria by which I am going to evaluate my ongoing actions, which is a little bit different framing. That's where what we thought we got out of that formulation.
Thank you. Yes.
You gave an example in that loop of a thermostat.
Yes.
But in the thermostat, the controller is set by someone.
Yes.
Deterministically.
Yes.
Adding supervisors to that in an almost infinite loop doesn't solve that problem. So what does adding more complexity solve if
it gives you
your underlying reality is still deterministic?
Well, the point is that you have systems that set the goal for the system. So in the monosynaptic feedback loop in the neuromuscular system, you have a gamma motor neuron that sets the criteria for the system. So the system's often this sets the criteria. What sets that criteria? Well, that criteria is set by other feedback systems, either within the spinal cord or within the brainstem and so forth. And each level of hierarchical loop is setting goals on the basis of greater complexity in terms of the whole organism, in terms of learning, in terms of past and future, and so forth. So you can get to the point where you have a cortical system or that is modulating goals of behavior at a very high and complex level, which is all I think you need for for moral agency, is to have very high levels at which goals are modulated.
But are those high levels, and here I'm coming back to one of your first points, are they ontological levels, or are they purely a way of describing things, being epistemic? And if they are epistemic, how does the downwards causation work? And if they're ontological, you're back with dualism.
The downward causation works by nesting, by lower level things being nested in larger patterns at higher levels. And so that's how downward causation works. Same with dynamic systems. That downward causation is not so much, and I'm not sure downward causation is even exactly the right word, because it's actually part-whole constraint in some sense. The smaller microparts are constrained by the larger pattern of the system.
But where then am I violating the laws of, let's suppose that there is some biological, like neurobiology determines our state of mind, right? The neurobiological makeup of our brain at any moment in time makes up the state. So what if that gives rise to these higher levels? When are these higher levels going to change how that, we still need a mechanism. And I intuitively, I quite like to follow your argument because I don't like determinism.
Yeah.
But we still, the levels in themselves don't get us away from determinism. We still need to break the determinism at the lowest level.
No, you don't. All you need is the deterministic systems at the lowest level to be nested in systems at the highest level that respond to the environment at the highest level, that interact with the environment as a whole system and interact with the environment in ways that embody meaning in that organization. Then meaning is involved in the organization of the entire system, which puts constraints on what happens at the micro level, but does not override them. So they can be determinist, stochastic, whatever you want, as long as they can be, their future can be influenced by the context in which they reside.
But if the micro level was deterministic, how, when is that? Because then that determinism needs to be broken at some time, at some moment, by those things at the higher level. So I'm studying this as Laplace's.
It's not
infinite
broken,
being.
it's constrained. It's not broken, it's constrained.
I think we'll need to discuss.
Unless you want to go to the philosophical position that absolutely everything in the universe is physically determined from moment to moment, in which case this conversation is meaningless.
Okay, that's actually what I wanted you to admit, that you need to break the determinism. And the loops in themselves don't get you away from the determinism.
Yeah, it depends on how determinate, well, I think they do, but I think there are emergent properties of systems that become causal in the world. And they actually interactively create causes. So we become social causes and we are influenced by social causes that can't be reduced. They are dependent upon and they are constraints of the micro-level systems, but as systems they become causally operative in the world.
Is there something like, you mentioned chaos at some point,
Yeah.
I think. I mean, are we getting into the realm of that somehow being, well, at least not but not deterministic either? Is that
Yeah,
necessarily?
I don't want to push chaos theory per se too far because I'll get beyond my expertise. I'm not a person who knows chaos mathematics well. I know its description from a sort of a systems point of view. So I don't want to push that too far because I don't know where we'll end up. Yeah.
Okay, so another one. Yes, at the back there. Yeah.
Just on the notion of chaos, I'm sort of in agreement with the gentleman down here, because I tend to think, I agree with you about the complexity that's being shown there. I remember reading James Blake's book on chaos theory, which is often put forward as an explanation of how we can have free will in a physical system.
Yeah.
James Blake, there's one sense where he says chaos theory is not intrinsically indeterministic.
Yeah.
And I take that to mean that chaos theory is so complex in the same sort of way that you've been showing that we can't possibly predict it unless we know absolutely every single parameter, which we can't do, we can't map that. And that's sort of the way I see consciousness and free will. To us, because we can't map every single parameter, it's unpredictable. It feels and it looks like it's free will, but actually it's completely determined because we can't map every single parameter.
Or it could be completely, or it could be non-determined. The point is we can't know. It's so complex. So.
Yeah, exactly.
Yeah.
Yeah. Peter.
I actually agree with these questions. I mean, I think you began by saying that you're going to leave to Nancy Murphy the philosophy, and now we're getting right
I know.
on the philosophy.
I know.
But I mean, these are big, deep questions. But it seems to me another smaller point where I think your presentation was not quite right, even though some of your conclusions were right, is your use of the word linear.
Okay.
Because I think you used it in three different ways. First of all, you talked about the philosopher Jaegwon Kim, and how he's talking about mapping between brain states and mind states, and he's asking the question, do the mind states do any real work? And he deals with that problem. And you referred to his way of talking about the problem as linear. Well, if that's going to be called linear, it's linear in the sense that there's a sort of he's considering the possibility of a one-to-one map between the mind states and the brain states. But
it's also temporally linear, I think.
Well, he doesn't. Oh, well, again, the way that historians use the word linear, yes, it's going from one point to the next. And then you indeed brought with the feedback systems a notion that was not linear in the sense that historians use the word linear, a linear view of history, because there's a recursive loop. But nevertheless, that seems to me a different use of the word linear. And then later in the talk, when you started talking about nonlinear systems, nonlinear, there you were using the word in the sense that mathematicians use the word, which means that y equals function of x, which is just not kx, it's a more complex function of x. So you've got three different notions of linear. And it seemed to me that in the last part of the talk, you brought out the value of a chaotic-like system for novelty, that it's not just doing the same thing over again, just in a loop that's going round and round and round. It's coming to forever new states, which is necessary for the system that's going to be novel. But it seems to me that although that's valuable, it's a different question from the one that you were dealing with earlier on Yegon Kim, and it's not clear to me really that you've answered the problem that he was posing.
Well, I would not disagree with what you said at all. The use of the term linear was different in different places. What we were trying to get away from in the philosophy of mind that was represented by that kind of work, and he's not the only one, a whole lot of people start talking about the philosophy of mind in those terms that just are not biological. It's just, I don't think you can get to an understanding of mind representing it that way. Brain state, mind state, one brain state leading to another brain state, one mind state leading to another. That you have to have you have to start your philosophy with a kind of system, with something like a biological system, which in essence is a feedback system, is a continually operating action loop. And you have to start your understanding of the possibilities for mind with respect to physical systems in that way. That was the move we were trying to make.
Thank you. Now, more questions. Let's run over that.
This is not looking for solutions, but at the end you outline three possibilities.
Yeah, those aren't exactly exhaustive, but that's
they're
the
kind
way.
of iconic
Yeah.
in a way. Can you say whether they're mutually exclusive or not?
Mutually exclusive. I don't think that there's a whole lot of nuances to that, so you could probably have 20 or 30 of those if you wanted to get real fine-grained about it. Physicalism and dualism, depending on the way you want to think about something like life after death, might not be mutually exclusive. That is, you might think about, and a lot of people do, a physically embodied person with respect to life here on Earth, and then some more dualist understanding of persons and that kind of. So perhaps those are not mutually exclusive. I think, and the determinism as a philosophical position, I think is mutually exclusive. What I've been trying to say is, I think you can have ruleful, micro-level systems that nevertheless, when constrained in larger complex systems that have emergent causal properties, that even though they may be deterministic at the micro level, the system as a whole operates with degrees of freedom and with causal properties that you can't find in the rulefulness of the micro level properties. So at that level of discussion, depending on what you mean by mutually exclusive, those statements are ways of organizing the world with respect to the general conversation about physical determinism and the impossibility of free will. Free will as represented within Cartesian forms of dualism versus a form of physicalism that we think can accommodate moral agency, free will, depending on exactly what we mean by free. And so those are, I don't know how totally, absolutely, mutually exclusive I say they are, but they do organize for me the options for a position with respect to human agency.
Good, thank you. Yes, yes, Lady Lo, yes.
Yeah, for complex systems other than the brain, do you think they have free will?
Oh man, I haven't. I think complex systems can be agents and can have causal properties that are not reducible. And we did not want the term free will in our title, to be perfectly honest. We wanted moral agency, but the Oxford Press wanted free will. And that, because free will is a loaded term in some respects, but I think you can have real emergent agencies in complex systems that are not physical and maybe and not human.
But is free will not essential for moral moral responsibility?
You have moral agency is, I think, what you're looking for. You're looking for a person who, as a whole person, is capable of making morally relevant decisions, but those are, for my money, are not totally free in the sense that we are not unembedded. That is, what we have to decide on the basis of has a lot to do with our history and our developmental history particularly, and the kind of things we read and know about, whatever that provides for us, the domains within which I have the possibility of choosing. So I'm an agent, but I'm not like I'm free to do something that is totally outside of my developmental history or my thought patterns or my personality. So
Yeah, there's a question. Yeah.
Did I get this right? Are you suggesting that complex IT systems can have agency?
Yeah.
Agency, yes. So for example, Mackay's little thing, he would say the very minimalist agent would be even a thermostatic system because it does something in the world agentive-like that is not done by the parts themselves, that once one organizes it the way it's doing something in the world based on information, it's processing information in a sense and responding to the environment based on this tiny little element of information. So, yeah.
A rather broad definition.
Yeah, it is. I mean, obviously you have to, but it gives a conceptual root in the way to think about agency that then only becomes rich enough to accommodate anything like human behavior when you begin to look at the complexity in the nesting and some other things.
Dennis had a question.
Yeah, well, it's just a point really on the previous question, and I wonder if a slightly different approach, but I just want to see what you think is. I mean, basically, free will, and I understand why you didn't want to use that in the title. It's a very slippery concept. But at the end of the day, it's an experience we have, isn't it? It's an experience. It's a primary experience we have of being free, and we give it a label, free will. And it just seems to be, and then the question is whether a non-reductive physicalist account of the world actually comes up with anything that would contradict that experience. I mean, that's a way, I guess, of framing the question, isn't it? So we start with our experience, which is what we do with everything else in the world, and then we ask the question whether there are things that actually might contradict that from our known knowledge of brain science and so on. And therefore, I guess the question about other complex systems is the question doesn't arise, as far as we know. So it's a non-question in that sense. I'm slightly defining the question out of, but you see, I think if one comes from that experience, then it's really a non-question because we are the only agents around that seem to have this experience, as far as we know. And if it wasn't the case, it would be hard to find out what those other agents.
In principle, what about artificial intelligence in principle?
Well, let me go back to Alicia Guerrero in her last chapter, which she's talking about free will, makes it clear that she doesn't think she's capturing everything about free, or these systems, their description, don't capture everything about human free will necessarily, but they do demonstrate a kind of causal agency of a complex system that is non-reducible and has the kinds of things that one would want to be in place for something like human free will. But I like the way you talk about free will is a subjective experience that we have that we wouldn't want to necessarily put on a non-human or non-biological system.
Okay, there's a question.
Our experience of free will may be illusory. We may have no choice but to believe that we have free will. But I'm sure that's not your position. But if it were the case, in what way would our neurobiology be different?
You would not have systems. You would not be able, for example, to do the dieter experiment. I don't think you would find that ability to talk to a person about the possibility of eating more healthy and these things are healthy and those things are not healthy, and then having actually used that to modify their evaluative systems in a way that's related to language input. I don't think that you could do that. Part of what I think you're talking about too is Wagner's work on the guy who talks a lot about automaticity and talks about he's really more interested in consciousness, but the fact that he thinks our feeling of conscious decision making is post hoc, that we do things and then we say that we decided to do that. And but most cognitive psychologists would say that is in fact the case in maybe 95% of our daily behavior, that we just do things, and if we ask why we did it, we post hoc get some reason for why we did it. But I think there is a possibility that we regularly, but not always, engage, which is the ability to reflect on our criteria, essentially reflect on our criteria for evaluation. That is, reflect on our goals and what we plan to do, and then we kind of make some adjustment, off we go, and everything's automatic. So that's part of the reason why the idea of free will sometimes carries the idea from that every aspect of my behavior is consciously a product of my conscious decision making. In which, in fact, we know that the majority of human behavior in any particular day is run off fairly automatically, but nevertheless, what the person essentially desires, in the sense that represents their behavioral criteria. But I do think we have opportunities. The whole mindfulness literature has to do with the ability, with the experience and ability and discipline of thinking about what you're doing on occasion, being reflective, consciously reflective. And I do think that begins to shift our criteria for evaluation at the highest level that has then all the downward implications.
Yes?
But if we can stick with the dieter example, you certainly implied that even the relatively high-level goal set was determined, and was determined by history, which is another way of saying determined by a whole series of sensory inputs over a long period of time. So even those higher-level goals you're implying were being determined by actually quite low-level inputs.
Well, I wouldn't use the term determined. We certainly are products of the influences of our involved in our history. But we also have the occasional experience of reflecting on those in some way, that that the person gets all this information about dying and sits down at some point and thinks, am I going to do this or not? And decides to do it. That begins to shift their criteria for evaluation. What comes after that may be entirely automatic in the sense of their dieting behavior, but it was a product of influence from social environment and some reflection on that.
Good. Yes, question there.
One of the attractions of functionalist theories of the mind is for people of religious persuasion is multiple realizability, that a person could be instantiated in silicon or in soul, some sort of disembodied soul. And it seems to me that these very embodied conceptions of personhood pose some problems for the idea that of continuity of the self outside of our current environment and physical embodiment. So, do you have any thoughts about how that
question? In terms of the resurrection.
Well, what represents me is the organization. The physical substrate obviously changes over time. So the molecules and whatever that are me are different than the molecules that showed up 3 years ago. But I think the organization of me as a person maintains continuity. And so what you would have to maintain is an organization.
I guess what I'm getting at is it's more the embeddedness, the extendedness of yourself, therefore, and your immediate environment pretty much determines who you are as well.
Well, the point for dynamical systems is despite the environment, the systems more and more respond to that environment from their own point of view, which is a historical point of view, but is still not necessarily determined by the environment, but is the environment related to me given my history.
Yeah, but isn't it just a question of time scale?
Yeah.
I mean, just that you can have simply slower time scale. I mean, that's a good adaptation. But in essence, this is not really different. Just to follow up on this question.
Yeah. How do you say this? It's psychologically naive to say that a person has choices that are not somehow had some prior representation in their experiences in the past. Whether those are determinative or not, actually some of them are and some of them aren't. They're all influences of things we know and things that we have experienced in the past, some of which are fairly strongly influential on me, and some of which are not necessarily. So I could think about them as possibilities and might even decide to do them, but they're not. The point I'm saying is that the possibilities out there, whether strongly or not so strongly influential, are only those which are related to my past experience. I can't think about something that is totally outside of some historical experience of some kind. Maybe I read a novel about it or something, but it is somehow. So to use the term free will as if one could do anything in the world is just psychologically naive. We have a realm of possibilities, but the question is, for me, are those possibilities in some times, in some ways, subject to arbitration of some kind? And I think the highest level systems we know become involved, the prefrontal cortex becomes involved when you ask a person to contemplate decisions.
I think we'll take one more question at this stage, and then we've got some refreshments. Okay, you're going to go back.
How does this, I'll ask you a completely different question now. How does this relate to your work on the corpus callosum, where people with split brain syndrome have been showing very interesting things in like moral differences between the two sides and religious differences between the two sides?
Wow.
How does that fit in with your type of research?
The two sides, they actually look the same.
Well, first of all, religious, I don't find that literature convincing at all.
Ramachandran's experiment.
Huh?
Ramachandran's
No.
experiment.
I don't find what Ramachandran does convincing at all. And there are differences between the two sides. I don't think they have anything necessarily to do with religiousness. Religiousness is something about the whole person, not one side of the brain or the other.
But he claims that he questioned the two sides.
I know, and he's just.
And he got different answers.
I know, and he's just over-interpreting his data, basically. What I would say about the people that I work with people who are normally intelligent and don't have a corpus callosum. And what happens with that, when you reduce the complexity of the brain by taking 200 million intercallosal neurons out of the equation, you have reduced complexity, reduced connectivity. And what happens with these people primarily is an inability, or not an inability, reduced ability to do complex, novel, rapid problem solving. So when you get a new situation that has novel demands, which and there is, particularly when there's some time demand, they are just not very good at it. But that same task, given enough experience and enough trials, they can learn to do it. So it's not like they can't do complexity, they just can't do novel complexity. So what this speaks to me is about the capacities that emerge from enhanced neural connectivity. When neural connectivity is reduced in certain ways, then the system has less ability to do computations rapidly at the moment, and some things don't emerge. So some of the things that don't emerge in agenesis of the corpus callosum is the ability to understand second-order meaning in language, metaphor, or humor, which is also a second-order meaning generally in jokes. They have a diminished theory of mind. I don't think theory of mind is a thing, but when you put them in theory of mind tasks, they don't do as well. They have problems doing word problems in math when they're in school, because that causes you to have to not just know about the mathematical solution, you have to imagine something about the relationship between this situation that's described in the problem and its relationship to a mathematical formula that you might be able to. So imagination and creativity are things they have problems with. They don't narrate social situations in a normal way. They leave out, when you ask them, we just published a paper on the thematic apperception test, which is a thing used by psychodynamic psychotherapists to kind of look at your psychodynamics or whatever, but they're socially rich stimuli that you tell stories about. And if you do a semantic analysis of those stories, their stories are absent in, or not absent, but diminished in emotional content, diminished representation of social process, and diminished representation of cognitive process, that is, the cognitive process of the people in the story that you're looking at. So the way I connect that with this kind of argument is that, for me, it's a suggestion of kinds of things that don't emerge in human cognitive process when you reduce the level of connective complexity. Well, there's also some right brain, left brain things, but those are actually less critical part of the story as far as I'm concerned compared to the diminished processing.
That's very interesting. Well, thank you very much, Warren. I mean, you've got off to a cracking start, and the stimulating